Hi, my name is Razvan Balasov. I'm a PhD student at the University of Bucharest. I work as a research assistant at the Institute of Space Science here in Romania. And I will talk about the black hole population simulations that we've been conducting here at the Cosmology and Astroparticle Physics Laboratory. Okay, let's begin. This talk is structured the following way. At first, I will talk about the motivation behind the study, then I will briefly describe the software package, and afterwards I will go in detail regarding the simulation parameters and goals, as well as underlining which results have or have not been accepted from a physical point of view by us. There are obviously next steps in stored, and considering the present work's results, we'll pursue them accordingly. So, we started to work on these numerical simulations due to several reasons. Admittedly, a very important factor was related to the LISA science objectives, with which we intersect substantially on many occasions. We do follow the black holes on their journey from their light and heavy seed scenarios until present day by taking into consideration growth methods. Obviously, the light seed scenario involves stellar origin black holes, therefore we'll have an input regarding the possibility of them being a real candidate for the first black hole populations. That supposedly led to the present day distributions. Clearly, there is a very important attention paid to gravity and how it affects the growth of the black holes until they can reach the needed orders of magnitude for their masses. And future scenarios will involve a lot more parameters compared to the number of ones used at this moment, one of which will surely be the rate of expansion of the universe. Our current understanding of the universe places these supermassive black holes in the center of most galaxies, as we all know. These compact astrophysical objects play an important role in galaxy formation and tracing cosmological structures. In order to provide the requirements for the LISA space mission, predictions regarding the black hole populations are essential. That is to say, investigating early universe black hole distributions will produce a higher chance of LISA observations in the future. The work presented here anticipates future simulations, which will in turn provide merger rates that directly involves LISA detections. Although there are various proposed mechanisms based on which the black holes grow, it is believed that the main growing mechanism is based on past generation mergers with the differences of evolution related to this initial seed black hole. The seed black holes scenario can be categorized as light or heavy. In the first case, the light seed scenario, the sources are a population of 3 stars, which form in a low metallicity universe and explode, forming a black hole with a mass of 2/3 of the original mass, on the order of a few hundred solar masses. In the second one, the heavy seed scenario, the black holes are already massive and were formed, for example, by collapse of protogalactic disks, and they have masses with orders of 10 to the 4 to 10 to the 6 solar masses. In this case, we used an n-body smoothed particle hydrodynamics code package named GIZMO, with the help of which we explored different scenarios for the first black hole populations. That is to say, black hole populations from the early universe, somewhere around 700 million years after the Big Bang. So we investigated the properties of these resulted populations from realistic black hole growth mechanism, merging to be in this case. This GIZMO is actually an open source package developed by Philip Hopkins from Caltech. It has descendancy from the Gadget software, which is a little bit more known, Gadget 2 to be exact. It draws a part of its code base from pgadget, and major differences between Gadget 2 and GIZMO are linked to the modules they provide. There's a lot of physics involved in GIZMO. GIZMO offers a considerable higher number of physics options. You can see right here on the slide: magnetic fields, conduction, turbulent diffusion, galaxy, star, black hole formation, feedback, a lot of physical modules. These are some examples of what the program can do, from cosmology to even cosmology is the first picture you see here in the table, and the last one, for example, is impact and giant impact like lunar formation. That's a simulation for that. So there's also black hole physics here at the fourth figure from the table, like AGN accretion resulted from gravitational capture. A lot of physics right there. So moving on to the study itself, we considered the resulted black holes from the heavy seed scenario, regardless how they formed, by presenting different simulations constructed in GIZMO. The differences between these simulations were represented by the initial conditions that we used. The purpose was to compare the generated results with the current massive black hole mass distributions. These distributions were obtained from a previous published catalog by Caramete and Biermann in 2010. The authors derived a black hole mass function, of the nearby candidates, of the nearby black holes. This is the source for the catalog right here on Vizier. And you can look it up by accessing the link on the slides. The present study was preceded by, of course, a benchmarking process and functionality testing. This calibration generated the baseline upon which more complex situations had to be built. We generated two main situations, two-dimensional and three-dimensional. Therefore, simple cases were used for that purpose, meaning that only gravitational effects were taken into considerations, and the results of the simulations had to be analyzed solely from that one perspective. Also, the reason behind the two-dimensional case was the need for preliminary testing and benchmarking regarding the particles itself. The particles have different parameters that we had to follow, and we wanted to be sure that everything goes smoothly. Okay, so these are examples of simulations, like initial conditions and final results after 13 giga-years of time steps, and the 3D case as well. Both cases show a clustering tendency, which is clearly unexpected behavior. Therefore, we moved on to a similar case, but this time with particles, with gas particles, for testing different aspects of the outputs that we had. You see the differences between the particles that are the type of gas and the type of black hole. They have different output files, and also wanted to make sure everything goes okay. So the red particles are the black holes, and the blue ones are the uniform distributed gas particles. Next up, so this is also the 3D case, part of the testing area, which allowed us to get as close as possible to the full distribution of black holes as inferred from observation. We when we started, when we finished the testing part and started the simulations, the real simulations, we decided to test 10 to the 5 solar masses as initial black holes, the case to begin with, and observe the subsequent numerical behavior across the span of these 13 giga years in order to reach present day. We set random values for black hole initial velocities, and we played around with the initial volume of the simulation. Moving on, the goal of this simulation was to obtain masses of 10 to the 8th solar masses for black holes. These had to be correlated with a concentration of 350 or 2,200 black holes per kiloparsec per cubic kiloparsec, derived from observations, the catalog that I mentioned before. And these concentrations are associated with the 10 to the 8th solar masses. Considering an extreme case where black holes grow by accretion at Eddington limit, simple computation estimates an approximate growth of 1 order of magnitude, so per 1 billion years. So taking account that a black hole can be in Eddington limit for too long, you have to provide new material for feeding after a new galaxy merger or new bulge forming, and that the main gravitational effects end after the first billion year in the universe, we place a limit of maximal accretion at Eddington limit at 1 billion years. So that is to say that by not taking into consideration accretion, the simulation should provide a growth from 10 to the 5 to 10 to the 7th solar masses by merging only. And then we add this 1 order of magnitude limit, and we consider that we reached 10 to the 8th solar masses. So this is the concept that we use. So we searched for the above mentioned concentration, and the way we did it is illustrated in these next figures. We started from an elementary cell that we let evolve through time and space. After the end of the time steps, we computed the resulted black hole concentration, taking into consideration only the masses with values over 10 to the 7 solar masses. This 10 to the 7 solar masses limit and the total spread volume. Due to the method that we chose, we had to use a scaling option that resulted that the concentration associated with the elementary cell volume, which is a cube with the side length of 10 parsecs, had to be multiplied until it reached the volume of 1 cubic kiloparsec. Thus, we scaled our result from the simulation without the need for more computing power that would match the exact same case. This is after going through a lot of situations, we decided to the two simulations should provide the baseline for our testing, and those two cases were these ones. One was with 4,000 black holes as initial conditions in a volume of space equal to 10 to the -6 cubic kiloparsecs. That's a cube side length of 10 parsecs. That took the end results to a concentration of 650 black holes per cubic kiloparsec, which is inside the limits that we wanted. The second case was we placed 1,700 280 initial black holes, 17,280 initial black holes that provided a final concentration of 1,800 black holes per cubic kiloparsec. Both results were well within the desired interval. obtained from the observations from the previous catalog. But here you can even see the evolution for both cases during this time span of 13 billion years. And you can even, it's a very visual way of actually seeing the space that gets filled after all these mergers. Now going back to the results, we wanted to, because the concentrations had good values, you know, in the interval that we searched for. You can see we started looking at the mass rate of growth. This figure presents the evolution of the merger rate, accumulated number for both cases, modeled with the power function that has, for the first case, for case with the 4,000 black holes as initial seeds, a slope of 0.54, and which is with blue. And the second one with red, a slope of 0.66. It can be noted that in the first case, the slope is much closer to the ideal value of 0.5, resulted from normal evolution of cosmological scale structures. Then we looked at mass distributions, again, for both cases. This is the first case, and this is the second one. And although both results were well inside the limits of the black hole mass concentration interval, we looked at these distributions and saw that the first case is closer to Gaussian distribution, suggesting a normal evolution, whereas the second one displays an exponential-like growth, followed by a quick descent. And the mass interval is larger than the observational data suggest, thus indicating a non-physical behavior. Therefore, the second case was eliminated. And that's a good thing, because this way we managed to find the initial black hole concentration in one of those two cases that generated the present distribution, as well as the merging rate for growth, which is a very important result for the LISA space mission. And in the future, this result will be used in the LISA collaboration for detection rate estimations and for a better preparation of the data acquisition and processing systems. And that I think my time is up, so that's all. So thank you so much.